So, transformer tap switching. That was the old transformer tap switch in that power supply. And okay, this was the relay that went with it. We don't need that anymore for the moment. And as a first step, I really would like to reverse engineer that. And yeah, EA branded. Yeah, I mean, looks simple enough, and maybe I can learn a little bit. We'll see. Oh, yeah, and how will I go about it? I do what the best on YouTube and probably worldwide do. Outside of YouTube, I will take a macro shot from the top, a macro shot from the back, mirror the back image, print both out, and then try to follow the traces and how they connect the parts. So, give me a minute or 2 or 10 or 15. So, the results are in. That was the top. I've looked up the 2 transistors they are using, and that was the bottom, just with a pen under it, so it's even on the surface, because the potentiometer here sticks out quite a bit. And yeah, it came out as that. And this is interesting. So they use all in all 16 parts to do the transformer tap switching. And here you go to the minus and plus binding post of your power supply, and we have here a nice voltage divider with the big pot, that one in the middle, so you have some room for adjustment. We have a Xenon diode, 6.8 volts, and a PNP transistor, and it's quite easy. As soon as the voltage is high enough here, at this point, that is at that point, that the Xenon voltage, so the 6.8 volts plus the whatever 0.6 volts here are reached, then the transistor becomes conductive, and that means we need here to switch on about 6.8 plus 0.6, 7.4 volts. And let's say that's exactly in the middle, and this is completely symmetric, so the switch point is at 14, if it's in the middle, 14.8 volts. Okay, that becomes conductive, and then we have this PNP over here, which then is switched on. Yeah, current is flowing through the base, and the PNP drives the relay, which has a freewheeling diode, okay, for not killing anything if it's switched off again. And yeah, that's basically it. Ignore that resistor and these resistors for the moment. The whole thing is powered by, that's interesting, one AC line from the transformer, from transformer winding going here. I call that AC live goes through two resistors, charges that capacitor, and this gives you your positive rail, which must have been around, you know, 16 volts or something from the capacitor rating, probably a little bit below. Yeah, that was okay. These resistors here, I'm not sure what they wanted to accomplish here with the 100 ohms. I mean, this thing might draw, if the relay is on, 20 milliamps to 25 milliamps, something like that. And yeah, this would give you a voltage drop across these two resistors of it's maybe 70 ohms, 80 ohms. I can't do the math right now in my head, but let's say 100 ohms and 20 milliamps. 20 milliamps times 100, 200. This gives you here a drop of, let's say, 2 volts at 20 milliamps. And that drop disappears, of course, if the relay is off or goes to something like 200 millivolts or 100 millivolts. Or no, it goes to basically nothing, because if it's off, neither that transistor is conducting nor that one. So yeah, limiting the inrush current to a 220 microfarad capacitor. I mean, that capacitor, to save the diode. I mean, the diode here, that's actually yeah, can you see it? That's a 1N. I can remove it now. A 1N004. 1N004. So that's good. That survives. I mean, easily. On switch on, worst case, yeah, but they limit the inrush current. Okay, whatever. That resistor here is a little bit more interesting, because my best guess is that makes sure, I mean, it's a relative high value compared to the on-state base resistor for the PNP. This is just there to make sure that the PNP is absolutely switched off, if that is switched off. I mean, if that was on, and there could still be, without that resistor, yeah, that missing that pass, there could still be some, yeah, that's normally a problem for MOSFETs, but there could be some charge here still letting some current through, or that resistor is not completely off, and then it trickles here down, and simply having your positive rail connected to the base via that 22K resistor will make sure that yeah, the base is at the same level as the sorry, I have to look it up. I always get things the emitter, yeah, as the emitter, and so it's switched off. Yeah, the other two resistors here are generating a hysteresis. So you don't want to wobble the relay to wobble around cluck, 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 cluck. If you go 14.7 volts, 14.9 volts, 14.7 volts, 14.9 volts, tuck, 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 you want some hysteresis here. So if it switches on 14.8 volts, you want the relay maybe to switch off at when it's going below 12 volts. And that's what these two resistors accomplish. If here our 20 milliamps, again 20 milliamps through the relay are flowing, you have a voltage drop over this, let's say 47 ohms at 50 ohms, so 50 ohms, 20 milliamps, 50 times 2 is 100, times 10 is 1. So if the relay is on and we have here that 1 milliamp flowing, you have here, you are 1 volt above the ground rail. And then if we have here a voltage drop of, let's say, 0.6 volts, then you have here an additional current flowing through the base from 1 volt minus 0.6 volts. Oh, that's complicated. Where's my calculator? Sorry. It's quite messy here right now on my desk. Ah, I see it. Ah. So, 0.4 volts divided by 150 ohms gives us, okay, times 1000, easier to read, gives us an additional current of, what was it, 2.7 milliamps here. And interestingly, I can't fathom, because 2.7 milliamps, I mean, we are here at 7.4 volts. If this is conducting, I'm just imagining the voltage here really goes down below the 7.4 volts. What will be the voltage that thing shuts off again? And that baffles me a little bit. Because this is simply flowing. Yeah, this is on now. This is flowing. And another, not an oddity, but a dirty trick. You see there is no, for the rectifier, single diode rectifier, there is no backflow through the transformer. Yeah, there's really only the AC live line going in. And so, yeah, where's the current flowing? Now we are here connected to the ground, to the negative of the power supply, and at some point somewhere we have a bridge rectifier. Oh, this is bad diode. This is positive. This is a negative, and okay, and we have here say AC live, and here we have AC neutral, and here we go to our not our positive rail. Here it goes to the regulator, but it's positive. And this here would go to our negative ground. Now you can see how the current is flowing from that AC live line from the transformer. I mean, what's live and neutral, it's arbitrary. It goes in here, charges the capacitor goes to the negative rail, goes to the negative rail through one diode of the bridge rectifier and to AC neutral. And yeah, these two ends are of course connected to your transformer. So yeah, that's just one wireless you need. Can do that. You don't have to, but you can. So that's an oddity, and in a minute I will look up what that relay, if it's still available somewhere, is actually drawing. Other oddities, and now it gets dirty. So, oops. So this resistor here, that 100 ohm resistor, that's that one here, that's 2 watt type. Okay, 2 watts. And this resistor, the smaller one in parallel, the 180 ohms, is a quarter watt type. And I said, okay, 20 milliamps. Let's say worst case, 20 milliamps are going through that 2 watt resistor. So 0.02 amps squared times 100 ohms gives us 0.04, 40 milliwatts. 40 milliwatts burned here. Yeah, if it would be 2 watts on that side, that would at least burn about 1 watt, which the little guy here wouldn't survive for long. So why would they use a 100 ohm resistor here? It absolutely makes no sense. It starts to make sense if you look at the resistors in our voltage divider here. Because the lower one, yeah, yellow, pink, brown, 470 ohms. That's also a quarter watt type, while the upper one, yellow, pink, brown, is also a 2 watt type. Why would you put a 2 watt type here and the quarter watt type here? And also, and little zoom work. Yeah, you see, it's too wide. It's too wide for the position. The position, yeah, they had really to squeeze it in and put it a little bit off board. I mean, it always looks like, okay, we run out of quarter watt resistors, so but we have some 2 watt resistors with the same value lying around, so use that. And you see, these are at least, you know, there's not a 2 resistors from the same series on that board. Not one. I mean, this is obviously from a different manufacturer than that one. That one is a nice oddity. The 2 watt types are completely different. And no, this is no special 2 watt resistor. This is also only, can I have some focus here? Yeah, 100 ohms, 5%. Yeah, 2 watt 5. It's nothing special. This is also a 5%. Oh no, it's actually silver. Okay. So, okay, these 2 resistors here, they look to be from this. No, they're not from the same manufacturer. Maybe, yeah. Maybe one pair of resistors is from the same manufacturer The others are, yeah, completely random. Completely random. And of course, the rectifying diode, sorry, zooming out again. The rectifying diode, focus, thank you. The rectifying diode, I lost it. Okay, doesn't matter. Oh no, it's still hanging on. It's botched on the backside over here. You know, to one of the AC lives coming in. Yeah, I don't get it. I don't. EA, look up the manufacturer. It's a big manufacturer nowadays for power supplies and stuff. Professional power supplies, industrial power supplies. And, I don't know. They started out in a garage, as it seems. Yeah, well, good for them. I look up the relay. Be back in a minute. So I couldn't find. I mean, these relays are obviously still sold as old new stock, but the manufacturer is obviously gone out of business. Yeah, can you read that? E-bolle. Yeah, they couldn't see. They're still doing some electric stuff, but more AC, mains AC installation. Couldn't find anything of them doing relays anymore. Yeah, and they were bought by another company in between. So I measured the DC resistance of the coil, which comes to 170 ohms, which is quite low for such a relay. That would make it at its nominated 12 volts to about 70 milliamps, which would then have a voltage drop around here over this resistor of 3.3 volts and provide, yeah, taking account the drop here. Anyway, till next time, when I will have come up with my own solution for a transformer tap switcher, hopefully, and maybe we can already prototype it. Wait, reading resistor values correctly helps. So this is 4 point, that was not a blob, 7 ohms. And that means here, even if we have 70 milliamps yeah, through the relay, that means we have here something like, yeah, probably the same, 0.07 times 4.7 equals 0.33 volts. Huh. And then a part, okay. So we have here, we must be here at 0.6 volts. And there is yeah, that's interesting, the feedback mechanism for to create a hysteresis, because that current is obviously flowing in this direction, because here at the base we should be here 0.6 volts over ground. And this is then 0.0, no, wrong again, 0.6 volts minus 0.33 volts. Something is amiss. 0.6 minus 0.33 equals. And we have here a voltage drop of 0.27 and divide that by 150 ohms. Then we're drawing a current here in the on state of 1.8 milliamps. This is valid for on. So we're stealing, as soon as this is on, we're stealing 1.8 milliamps here away. But if we are in the off state, yeah, the 70 milliamps are not flowing here, and we don't have that much of a voltage drop over that 4.7 ohm. Basically, we have comparable no voltage drop. So that would be in the off state. Again, assuming we are here about 0.6 volts. In the off state, we would be stealing away 0.6 divided by 150, 4 milliamps. Okay, and that makes a lot more sense to create a hysteresis. So at that point, if it's off, we have to provide a little bit more current here to switch it on, because when we're reaching the 0.6 volts, until we reach the 0.6 volts, we are stealing here to ground 4 milliamps. As soon as it switches on and current flows through the relay, through the resistor, we lift that point up a wee bit, 0.33 volts, and then we are stealing only 1.8 milliamps away. Okay. I can guess you, yeah, you can do this, but still, please comment on this contraption down below the video. Click on comment. Okay, so now I understood what's happening here, and yeah, I don't need to get that thing working again to probe on it. That's a relief. Okay, so finally, bye.